In this video, we're going to see capacitances in PN junction. There are two kinds of capacitances in PN junction, namely one, depletion capacitance, and two, diffusion capacitance. We'll start with understanding depletion capacitance first. To start with, let me take a PN junction where I'm taking reference voltage as V suffix D across this PN junction, where Vd represents the voltage across the diode. If we take a Vd in this axis, where let's say Vd is 0 here, which means in this region Vd is positive and in this region Vd is negative. I am assuming that we are applying a voltage of this value, which means we are applying a negative value of Vd, which indicates that this PN junction is reverse biased. And let's say this is the depletion width corresponding to that applied voltage. Let's say that is W, and the depletion width on P side, let's say, is XP, and depletion width on N side is XN, and this is the total depletion width at the PN junction. And this is how the charge concentration is distributed, and this is how the electric field in the PN junction is present. This magnitude would be Q times Nd, where Nd is the concentration of doping on N side, and the magnitude here would be minus Q times Na. Na is the doping concentration on P side, and this is Xn, and this would be minus Xp. And this value here is 0 for the X, where we are measuring the distance. Electric field, we have maximum electric field right at the metallurgical junction, which is directed from N side to P side because the charge on N side is positive and charge on P side in the depletion region is negative. So electric field is pointed from positive to negative. This area should be equal to this area, where we can write the equation to be QND times Xn should be equal to QNA times XP. And we know that Emax is actually given by minus QNDXN over epsilon. And of course, we can replace this NDXN by NAXP as well. Now coming to the property of capacitance. Capacitance is nothing but ability to store charge for an applied potential. In this case, if we see that the PN junction is able to store charge in the depletion region, which is immobile in nature, for a given applied potential. But in general, if we talk about capacitance, C is actually given by the total charge stored per given voltage. C is equal to Q by V. But in this case, we are not actually interested in how much is the charge stored in the PN junction for the applied voltage. Instead, we are actually interested in finding out, for a change in the potential, how much is the change in the charge stored in the device. That is the capacitance which we are interested in. And this capacitance, we would call this as small signal capacitance, because practically when we use PN junctions in analog circuits, basically we apply a DC potential for biasing, and on top of it we apply a small signal which is AC in nature. As a result, we are modeling the PN junction capacitance according to small signal, so that in analog circuits we can use this model. But it might not be just the PN junction, because there are a lot of other devices like JFET, MOSFET and BJT where you have PN junctions. So we need to understand how the charge changes when the AC voltage is changing. So that's why the capacitance, which we are calling small signal capacitance, is more important. This figure is shown for a voltage that we applied minus V. Let's say we change the potential by del V, then the potential here modified one would become minus of V plus del V. Because the reverse voltage is increasing, the depletion width would increase. Now let me represent that here. So depletion width would increase on P side, and on N side it would increase more because the doping on N side is less compared to P side. Charge distribution would become like this. So the extra charge that we got in the depletion region, I'm representing here, and the distance on N side, the depletion width on N side, would change from xn to xn plus, let's say, del xn. And similarly here, this point would be minus of xp plus del xp. Now we can write the relationship of increased charge as q nd xn plus del xn should be equal to q na xp plus del xp. We can rewrite this expression as q nd del xn should be equal to q na del xp. In a similar way, the electric field will also get modified like this. The electric field in the junction would increase this way. So new Emax would be there, which would be equal to Q nd xn plus del xn over epsilon. Now our interest would be to find what is this del Q. So let me write what that del Q is. It is the charge that has changed because of the change in the potential that we applied across the PN junction. So we can write the total charge increased as Q nd times del xn times the area. Area is nothing but the cross-sectional area of the PN junction diode. So to represent, let me take the diode is like this, and these are the two terminals. Then this is the area I'm talking about. This is the cross-sectional area of the PN junction diode. So this would be the charge. Now let us look at the units. ND units would be number per centimeter cube, and del x would be centimeter, and A would be centimeter square. Centimeter cube gets cancelled, and we have Q times number, which means it tells the amount of charge changed because of the change in the applied potential. Now the C can be written as del Q is equal to Q nd del xn times A over del V. Now we can rewrite this capacitance C as Q nd A times del xn over del V. Now if we apply limit that del V tends to 0, just this del xn over del V can be written as del xn over del V, partial differentiation of xn over the applied potential. And this potential is basically Vd because that's the voltage across the PN junction diode. So now we can write this capacitance as Q nd A times del xn over del Vd. Xn we know can be written as Na over Nd plus Na times W. And we know the formula for W, which is 2 epsilon naught epsilon r over Q times Nd plus Na over Na Nd whole power half times Vbi minus Vd whole power half. Now we need to find what is del xn over del Vd. We can write this as partial differentiation of xn with respect to Vd would be this value. Once we know this value, we can substitute this into this capacitance equation. The C value would be this. But it is surprising to see that we get a minus sign. But in fact, the capacitance definition is the amount of change of charge stored per the change of voltage applied. We're talking about just the quantities. So we really don't care about the minus sign. So we should be taking a magnitude here. We can rewrite this expression as epsilon naught epsilon r times A times Q over 2 epsilon naught epsilon r times Vbi minus Vd times Na Nd over Na plus Nd whole power half. And this quantity, which we know is 1 over the depletion width W at the applied potential Vd. So we can write this capacitance as epsilon, as we can write epsilon naught times epsilon r as epsilon times A times 1 over W. So we write it as by W. Of course, we know this is small signal capacitance, but this is in specific relating to the depletion region charge. And we can call this as a space charge. And we can also call this region as transition region because this is the region through which we are transitioning from P to N or N to P. So we call this a transition region as well. So we can call this capacitance as depletion capacitance or transition capacitance or space charge capacitance. We'll name it as C suffix T, representing transition capacitance. And we will reserve the C suffix D for the diffusion capacitance that we will discuss next. This equation looks very familiar. We know that parallel plate capacitor also has this similar formula where we have two plates in parallel where each plate is of area A and the distance between the plates is W, and these are the two terminals. We can say the capacitance of this parallel plate capacitor as C is equal to epsilon A over W. So which means even though we did a lengthy derivation, it's a very simple thing to remember because we can assume that the depletion charge is actually present on these plates which are separated by a distance of W, which in our case is depletion region width. And the cross-sectional area is actually the area of the PN junction diode. Now let me explain the second capacitance that we said is diffusion capacitance. To start with, let me take the same PN junction where the voltage we are applying is VD, and for reference let's say this is 0 for VD line, and now I'm assuming that we are applying some positive voltage across the PN junction. And to represent the forward bias, I've reduced the depletion width here. When we forward bias, what happens in terms of current components is that the majority carriers holes on P side would get injected onto the N side. And once they go there, they're basically minority carriers in the N side. And deep into the N side, the carrier concentration of minority carriers would be very small. As a result, there is concentration gradient of the holes in N side. So the holes would diffuse deep into the N side. When they do so, they recombine with the majority carriers, electrons, and the concentration of injected holes would decrease as they go deep into the N side. If the length of the neutral N side is long enough, then none of the holes might actually go to the end of this N side. This process of injection would be continuously happening and recombination would be continuously happening. As a result, the injected hole concentration with respect to time would not be changing. And similarly, the electrons would be injected into the P side, and the same scenario happens that electrons would see a concentration gradient and they try to diffuse, recombine with the majority carriers holes, and the injected electron concentration would be decreasing as they go deep into the P side. For a given voltage, the process of injection, recombination would be constantly happening. As a result, the concentration of excess electrons in the P side wouldn't change with respect to time. Now let me represent the concentrations, how they are changing with respect to distance. This is how the minority carrier concentration would look like in the PN junction. So the y-axis is minority carrier concentration and x is the distance measurement. This is hole concentration on N side, which is Pn of x, and this is electron concentration on P side, which is Np of x. And Pn naught is the equilibrium hole concentration on N side, and Np naught is the equilibrium electron concentration on P side. While deriving the diode current equation, we found the expression for Pn of x. I'm taking that value, which is Pn of x given by Pn naught plus Pn naught times e power v by Vt minus 1 times e power minus of x minus xn over Lp, where Lp is the diffusion length of holes. You can see that at x equal to xn, the concentration this point would be equal to this Pn naught plus this value, which means this value is nothing but the del P, which is actually injected into the N side right at the edge of the junction. So this value is del P, which is given by this. For a given voltage, this is how the concentration looks like, which means we are actually storing this minority carriers in the PN junction. So we can say that this total number of holes with respect to time, they are not changing, which means they are actually present inside the diode. And similarly, we are storing the electron concentration, which is the injected electron concentration. The concentration that is stored would depend on the potential that we apply. And definition of capacitance is basically how much charge is stored per applied potential, which means we see a clear capacitance in this case. And we're going to call this capacitance as diffusion capacitance because the stored carriers are actually diffusing in the neutral material. And we're going to define the diffusion capacitance, and that too, it should be a small signal capacitance. So we write it as a del Q by del VD, del Q by del VD. And as del VD tends to 0, we can write this also as del Q over del VD. Instead of changing VD by just del VD and then finding out how much is the change in the charge stored, we'll simply find what is Q as a function of applied potential and then do derivation in order to find the capacitance. So now to start with, let me find what is the charge, which is the excess hole concentration in the N-side material, which would be given by the excess carrier concentration is given by Pn of x minus Pn naught is equal to, this is the excess carrier concentration given by Pn naught times e power V by Vt minus 1 times e power minus of x minus xn over Lp. Pn of x minus Pn naught would give us the excess hole concentration in the N side. And we need to find the excess charge concentration in the N side. To find excess charge concentration, we need to multiply this with Q so that the expression would become Q times Pn naught times e power V by Vt minus 1 times e power minus of x minus xn over Lp. This is the excess charge concentration, but we want excess charge. So we would multiply this with the cross-section area of the PN junction. The units of this one would be charge per length. Now in order to find the charge, we need to find the total area under this curve. We can find that by doing integration. So we're going to do integration to this from xn to infinity, because anyway this curve would go to 0 before we even go out of n region. So taking limit to infinity wouldn't make a difference. So once we take limit from xn to infinity, we can take all the x independent terms outside, which is a q Pn naught times e power V over Vt minus 1 times e power xn over Lp, and we are left with e power minus x over Lp inside times dx. The integration of this function, the value would be equal to simply e power minus xn over Lp times Lp. So now we can multiply this with these terms. E power xn over Lp and e power minus xn over Lp gets cancelled. So now the whole charge on the N side would be equal to, if you do the similar procedure to find the excess electron charge in the P side, we would get Qn is equal to Q times A times Np naught times Ln times e power V over Vt minus 1. In fact, we know the current because of holes Ip can be written as Q dP Pn naught by Lp times e power V over Vt minus 1, and In can be written as Q dN Np naught over Ln times e power V by Vt minus 1. We can write Qp in terms of Ip as L P square over dP times Ip, and this can be written as, we know Lp is square root of dP tau p, So LP square would be dP times tau p, dP cancel, and we will have tau p times IP. And similarly, we can write Qn as ln square over dn times In, which is equal to tau n times In. We can understand conceptually how they are related. The current basically gives us the hole current, the number of holes flowing per unit time multiplied with the average time that holes would be alive before they recombine. So the number of holes coming per unit time multiplied with time, we'll have the number of holes, and that is what we computed QP. And similarly, we can understand for Qn. And now the total charge is equal to QP plus Qn, that is stored in the PN junction diode, which would be equal to tau p IP plus tau n In. And we know that IP plus In is actually the diode current which is flowing, ID. We'll write the total charge as tau suffix t times ID, where tau suffix t is the mean transit time, and the relationship between this equation and this equation is beyond the scope of this course. So we wouldn't discuss how to get tau t in terms of tau p and tau n. And we know the expression for ID, which is given by I naught times e power of v over vt minus 1. If you take the diode to be non-ideal, then we would have a eta. And v can be substituted by vd, which is nothing but the diode voltage across the diode. Then we can find the capacitance, which is del q over del vd. If we do that to this q equation, we will get tau t times, if we differentiate I naught times e power v by eta vt minus 1, we would get I naught times e power v over eta vt times 1 over eta vt. And we can say this equation is approximately equal to the diode current itself. We can write the expression for the capacitance, and we call this capacitance is diffusion capacitance. So let me say this C suffix D, which is given by tau suffix T times the diode current ID over eta Vt, where Vt is the thermal voltage and eta is the ideality factor. For germanium, it will be 1, and silicon, it will be 2. Now let me put up the transition capacitance equation along with this, which is epsilon A over W. Let me compare both the capacitances, how they are changing with respect to the applied voltage across the diode. In order to do that, let me take CD can be said as directly proportional to exponential of the diode voltage over Vt. And we can add eta as well, which means the capacitance would exponentially increase as Vd increases, and assuming Vd is positive. And Vd is negative, basically CD would be diminishing to 0. Whereas for CT, we can write it as directly proportional to 1 over, we have a square root of VBI minus VD in the depletion with W. So I'm going to write this as square root of VBI minus VD. Let me plot these two capacitances with respect to VD. The curves for CD and CT with respect to VD would look like this, where in the reverse bias, VD is negative. The dominant capacitance is CT because CD is pretty much 0 in this region. So in general, people call CT also as a reverse bias capacitance because that's the dominant one in the reverse bias. Now, whereas when VD is positive, so when we have forward bias, of course, both the capacitances are present. The reason why CT is present is because it depends on depletion width. If depletion width decreases, then CT is pretty high. That's why CT is basically increasing in forward bias. But at the same time, CD is an exponential function. So CD increases like anything as we increase VD. So in forward bias, the dominant capacitance is CD, the diffusion capacitance. In terms of magnitude, it will be in orders of magnitude difference. As a result, we can neglect CT in forward bias. And in general, people call CD as forward bias capacitance.